Assalamu alaikum students. I hope now you know the difference between a sequence and a series. A sequence is a list of numbers in a definite order, while a series is a sum of terms of a sequence. Whenever we talk about a series, two questions arise. The first question is whether the series converge or diverge, and the second question is if the series converge, what is the sum of the series? So far, we have been able to find the sum for two series. One is the geometric series, whose sum is given by the formula a over 1 minus r, while the second series is 1 over n into n plus 1, whose sum is 1. This is because in each of these cases, we can find a simple formula for the nth partial sum Sn. So it's not very easy to compute the limit of the nth partial sum. So in the next few sections, we develop several tests that help us to determine whether a series is convergent or divergent without explicitly finding its sum. So first test involves improper integrals, and this test is called integral test, and this is 11.3 section of your book Thomas Calculus 11th edition. And in this section, you will learn how to find convergence or divergence of a series by using integral test. So what is an integral test? Let's see. Suppose f is a continuous positive decreasing function on the interval 1 to infinity, and let an is equal to f of n. Then the series summation an is convergent if and only if the improper integral f of x from 1 to infinity is convergent. So in other words, integral test is you are given a series whose nth term is an. You write a function with this defined by this series, that is f of n, and you write the function as f of x. Now this f of x should satisfy three conditions. The first condition is f should be continuous. Second is it should be positive, that is it must lie above the x-axis, and the third is it should be decreasing on the interval 1 to infinity. If these three conditions are satisfied, then you can apply the integral test. And the integral test is you have to evaluate the improper integral with the integrand f of x over the interval 1 to infinity. Now you know how to integrate an improper integral. If the improper integral is convergent, that is if you can find a finite number for this improper integral, then the series is convergent. And if the improper integral is divergent, then the series is divergent. Now there are two important points you need to remember. The first point is that is when we use the integral test, it is not necessary to start the series or the integral at n is equal to 1. For example, if we have to find the sum of or convergence of the series 1 over n minus 3 square from n is equal to 4, then we have to evaluate the improper integral from 4 to infinity, not from 1 to infinity. And the second point is that is, it is not necessary that f be always decreasing on the whole interval 1 to infinity. The important thing is that f must be ultimately decreasing, that is decreasing for x larger than some number n. That is, they must be decreasing after some number n, and before the number n, they may be decreasing or increasing. But we are concerned with all the values of x that lie after the number capital N. That is, they must be, you can find a number n that is after this number x. For all values of x larger than this number n, f must be in decreasing. That is, f must be eventually decreasing or ultimately decreasing. Then the series is convergent from n, capital N to infinity, and this convergence is given by the note of the section 11.2. Now the example 1 is show that this series is convergent. Determine whether the series given by this 1 over n square plus 1 from 1 to infinity is convergent or divergent. So I will find its convergence or divergence by using the integral test. For the integral test, I have to write a function from this series, and the function is given as f of x is equal to 1 over, instead of n, I will replace n with x, that is 1 over x squared plus 1. Now first I will check the three conditions. The first condition is that f of x should be continuous on the interval 1 to infinity. Now f of x, which is given by this, is continuous on this interval. You can check it easily. Also f of x is, that is f is continuous, f is positive, that is x is positive, x squared plus 1, and 1 over this is positive, so f is positive on this interval. And the third condition is f should be decreasing. Now when I increase x, f of x is the reciprocal of x squared plus 1, so f is a decreasing function on the interval 1 to infinity. Now I can apply my integral test, because f satisfies all the three conditions. So the integral test is, I have to compute this integral, improper integral 1 over x squared plus 1 from 1 to infinity. Now this improper integral is evaluated as limit t approaches to infinity from 1 to t, 1 over x squared plus 1 dx. Now integral of this is 1 over x squared plus 1 is, all of you know that this is tan inverse of x, limit from 1 to t, limit of integration. So it becomes tan inverse of t minus tan inverse of 1. Now tan inverse of t is what? Tan inverse of t when t approaches to infinity is pi by 2, and tan inverse of 1 is pi by 4. So it becomes pi by 2. So my integral is, improper integral is a finite number. This implies that the integral from 1 to infinity f of x, or 1 over x squared plus 1 dx, is convergent. This is convergent. So by integral test, my series which is given by this function, that is 1 over n squared plus 1 from 1 to infinity, is also convergent. So this is how you use the integral test. Now the next example, example number 2, and example 2 is, you are given a series 1 over np, where n is from 1 to infinity, and you have to find those values of p for which, where p is a real number, for which this series is convergent. So before I apply the integral test, I will remember the divergence test for the series, and the divergence test for the series is that if limit a n when n approaches to infinity is not equal to 0, that is, it is other than 0, then the series a n is divergent. This is the divergence test for the series. We did it in the last section, the previous section, that is 11.2. Now let me apply the divergence test for some values of p. That is, if my p is less than 0, then what is the nth term np, and n approaches to infinity, the limit of the nth term. Now my p is negative. If my p is negative, then taking this p in the denominator, the power of n becomes positive. That is, when n approaches to infinity, it keeps on increasing. So this is equal to infinity. That is, it is divergent. And also, if p is equal to 0, then my nth term is 1 over n power 0. That is 1 over 1, and n approaches to infinity, it becomes 1. That is, it is not equal to 0. This implies that for p less than equal to 0, my series 1 over np is divergent. So let's see how does this series behave for the values of p greater than 0. So far I have not applied the integral test, but for the values of p, the values of p greater than 0, I will apply the convergence test. Now for p greater than equal to 0, my f of x, I will apply the integral test. For the integral test, I have to write the f of x, and f of x becomes here x power p. Now I have to check the three conditions for this f of x on the interval 1 to infinity, or any finite number. Now since this f of x is equal to 1 over xp and p is positive, so whatever the x is, because x is from 1 to infinity, so it would be always positive. So the terms f is, it is always continuous, positive, and also it is one reciprocal of this xp, so it is a decreasing function. Decreasing function on the interval 1 to infinity. So I will evaluate the improper integral. All the three conditions are satisfied, so I can apply the integral test, and the integral test is I have to evaluate the improper integral 1 over xp dx. And what about the convergence and divergence? We have studied the convergence and divergence of this improper integral in the section 8.8, and in this section we learned 8.8, that is improper integral, and in that section we learned that this is convergent if p is greater than 1, and this is divergent if p is less than equal to 1. So this implies that the series 1 over np, by integral test, the series 1 over np is convergent for p greater than 1 and divergent for p less than equal to 1. So if p is equal to 1, then my this series becomes 1 over n, which is harmonic series. So this we also know that the harmonic series is divergent, and from the integral test it is also clear that for p is equal to 1, this series is divergent. Now the series in the example 2 is called P series, and it is very important. The rest of the chapter we will be using the result. So I will summarize the result of this example 2 as this, as result 1. The result is the P series given by 1 over NP from n is from 1 to infinity is convergent if P is greater than 1, and it is divergent if P is less than equal to 1. Next example is example 3a. Now the series 1 over n cube, n is equal to 1 to infinity, is a P series with P is equal to 3, and 3 is greater than 1. So this series is convergent. So we don't need to prove the series to be convergent. We just apply the result and show that it is convergent. The next example is the series 1 over n power 1 over 3, where n is from 1 to infinity. Now this is a P series with P is equal to 1 over 3, which is less than 1. So this series is, by the result 1, this series is a divergent series. Now there is one more important point, and the point is that is the sum of the series is not equal to the value of the improper integral. That is 1 over n square is basically summation 1 over n square is pi square over 6, while when we integrate it, this improper integral 1 over x square dx will get 1. So in general, the sum of the series is not equal to the value of the improper integral. Although the convergence of the improper integral implies the convergence of the series, but the sum of the series is not equal to the value of the improper integral.